The ground beneath your feet feels solid, stable, as if it has always been there and will remain there forever. But that sensation is a remarkably subtle illusion. What you are actually standing on is nothing more than a thin layer of rock, almost negligible in thickness, floating atop an ocean of hot metal, itself wrapped in an atmosphere so thin that, when viewed from afar, it nearly disappears. Everything familiar to us exists within a structure far more fragile than our intuition ever suggests. When Earth is seen at the correct scale of the universe, the feeling of home is never quite the same again. And if you continue forward with me, layer by layer, you will see why something almost invisible can carry such immense significance. The sense of certainty the ground provides is so strong that it is rarely questioned. When we stand still, the rock beneath us does not shake, sink, or flow. And so, the human brain automatically treats it as an ultimate foundation, something absolutely reliable. But this sense of stability does not arise from Earth's physical reality. It comes from the limits of human perception. We experience the world on the timescale of heartbeats and footsteps, while this planet operates on timescales of millions of years. Where movements too slow to notice are the very forces that reshape entire worlds. If Earth were shrunk down to the size of an apple, the layer we live on would be thinner than the apple's skin. This is not poetic metaphor, but precise geometric proportion. Earth's radius is about 370 kilometers, while the average thickness of the continental crust is only a few dozen kilometers. In other words, if Earth were a sphere 1 meter in diameter, the entire space humanity has ever inhabited would be only about 0.5 millimeter thick. A light scratch on the surface of that sphere would be enough to erase every city ever built, every language ever spoken, every memory ever recorded. Another way to visualize this is by comparing Earth to the human body itself. The skin on your palm is about 1 to 2 millimeters thick. It shields bones, blood vessels, and nerves beneath, giving you the sense that your body is a unified, stable whole. But a small cut is enough to remind you how fragile you really are. Earth's crust plays a similar role. It is the only barrier separating the living world from material so hot that direct contact would instantly destroy all biological structures. Humanity survives not because this skin is thick or strong, but because it is not yet torn. Human attempts to pierce this skin expose that limitation clearly. The deepest hole ever drilled, the Kola Super Deep borehole, reached just over 12 kilometers. That sounds impressive until it is placed beside Earth's radius. If the planet were an apple, that borehole would be nothing more than a faint surface scratch, so shallow it would barely be visible. 2 decades of labor, thousands of tons of steel, countless engineering innovations yielding only the lightest touch on the skin of a world we call home. We are stopped not by distance, but by heat, pressure, and the nature of matter beneath our feet. This becomes even clearer when we look at familiar phenomena that are often misunderstood. Mountains, symbols of permanence and solidity, are in fact mere wrinkles on the planet's surface. The Himalayas, rising more than 8,000 meters above sea level, amount to little more than the thickness of a coat of paint compared to Earth's radius. If Earth were a basketball, the Himalayas would be almost impossible to feel by touch. Mountains persist for tens of millions of years, not because they are immobile, but because they are continuously pushed upward from below while being eroded from above. They are not still. Their motion is simply slower than our senses can detect. Beneath these wrinkles lies the mantle, a vast mass of hot rock that is not solid in the usual sense. It does not flow like water, yet it does not remain rigid like cold stone over millions of years. It bends, ices, and sinks, carrying tectonic plates like ice flows on a dense ocean. When two plates collide, the surface crumples into mountains. When they separate, magma rises to form new crust. When they slide past one another, energy builds up and is released in seconds, shaking entire cities. Earthquakes that seem sudden are in fact the result of centuries of silent movement beneath our feet. Deeper still, Earth's liquid metal core churns continuously, generating the magnetic field that envelops the planet. This field cannot be seen or touched, but if it vanished, Earth's surface would quickly become as hostile as Mars. The solar wind would strip away the atmosphere. Cosmic radiation would flood the surface, and the thin skin on which life clings would lose its protection. What keeps the air in place? The water from being blown away, and life itself continuing, lies deep below, in a region humans have never reached and likely never will. Seen this way, an unavoidable truth emerges. Humanity does not live on a permanent foundation, but on the thin skin of a geologically living body. We like to think we dominate the ground building, digging, extracting, but in reality, we are merely taking advantage of a brief period of stability in the history of a constantly moving world. The stability we perceive is not a natural state. It is a temporary balance between immense forces quietly at work beneath us. And once this is understood, the question is no longer how large Earth is, but how something so thin, so fragile, can serve as the foundation for all the life we know. Understanding this skin is the first step toward understanding why this planet, though small and delicate, carries significance far beyond its physical size. There is a simple thought experiment that becomes deeply unsettling if you dwell on it long enough. Imagine compressing the entire Earth into an apple placed on a table. Mountains, oceans, deserts, cities, everything scaled down proportionally. In that image, the apple's skin represents Earth's crust, the stage upon which all human history unfolds. The problem is that even an apple's skin is still too thick. At the correct scale, Earth's crust would be thinner than the glossy wax coating sprayed onto apples in supermarkets. All wars and religions, science, art empires rising and falling. Cities of tens of millions are confined to a layer of rock so thin that if Earth could be held in one's hand, a careless touch could scratch it away. Our sense of the world's depth is an illusion. The deepest cave ever explored, Veryovkina Cave in Georgia, descends just over 200 meters. The deepest borehole in history, the Kola Super Deep Borehole in Russia, took more than 2 decades to reach 2 kilometers before it had to be abandoned. These numbers sound vast until compared to Earth's radius of nearly 400 kilometers. The ratio between the deepest point we have reached and the planet's center is so small as to be almost meaningless. Geometrically speaking, humanity has never pierced the planet's skin. Beneath that seemingly immobile crust lies a completely different world. Not a hell in the religious sense, but an ocean of hot rock where matter behaves neither like solid stone nor like liquid. The mantle, which makes up more than 80% of Earth's volume, flows slowly on geological timescales at just a few centimeters per year, slower than fingernails grow, yet powerful enough to bend continents, raise mountains, tear oceans apart, and reshape the entire surface of the planet over millions of years. Humanity lives on floating rock, literally, not metaphorically. Tectonic plates truly float atop the hot, ductile mantle below, like ice sheets on a dense sea. The stability we feel exists only on the time scale of a human lifetime. over longer timescales. No continent stays put. No ocean lasts forever. And no coastline is guaranteed. There are places on Earth where the boundary between the familiar world and the planet's interior becomes frighteningly thin. Iceland is one such place. There, two major tectonic plates are pulling apart right at the surface. A person can stand in the rift, placing one foot on the North American plate and the other on the Eurasian plate. This is not symbolism, it is living geology. Beneath lies magma. Above is cold air. And humanity stands wedged between two slow but unstoppable motions. This fragile crust is precisely what allows life to exist. Not too thick to be isolated from internal energy. Not too thin to be destroyed constantly. Volcanoes, earthquakes, and plate tectonics are not unfortunate side effects of Earth. They are necessary conditions. Without volcanism, the atmosphere would not be replenished. Without plate tectonics, carbon would be permanently locked into rock, pushing the climate beyond the limits life can tolerate. Earth's stability does not come from stillness, but from a finely balanced chain of instabilities. This thin skin is also humanity's hard limit. At ocean depths nearing 11 kilometers, pressure can crush steel, just a few dozen kilometers into the crust. Temperatures exceed the tolerance of any machine we have ever built. All plans to dig to the center of the Earth exist only in fiction. In reality, humanity is trapped on the surface like bacteria living on the skin of an apple, unaware of what lies inside. This leads to an intriguing paradox. We understand the surface of Mars in greater detail than the structure of the mantle directly beneath our feet. Maps of Earth's ocean floor remain cruder than maps of the Moon's surface. There are mountain ranges beneath the sea higher than Everest, valleys deeper than the Grand Canyon, existing in perpetual darkness, never once seen directly by human eyes. If the crust is the skin, then the atmosphere is the breath, and that breath is so thin it nearly does not exist when viewed from space. Most of the air you inhale each day lies within a layer less than 20 kilometers thick above the surface, compared to the planet's nearly 13 null-kilometer diameter. This layer is a faint blur. From the International Space Station, astronauts can see the atmosphere as a pale blue curve, hugging Earth so tightly that it looks more like a visual artifact than a real structure. There is a detail many astronauts describe using the same word, vulnerable. Not because Earth looks small, but because everything that protects life appears alarmingly fragile. There is no glass dome, no roof, no sharp boundary between here and death. Only a thinning layer of gas that gradually fades into nothing. That psychological response has a name, the overview effect. A shift in perception that occurs when viewing Earth from the outside. Many return with a new understanding every conflict, every border. Every dispute takes place within a layer so thin that it offers no justification for human arrogance. The crust and the atmosphere are not only thin, they are finite. They cannot be expanded. They cannot be replaced. There is no backup version of the atmosphere. Every molecule of oxygen ever breathed has passed through the lungs of countless organisms before. Every drop of water that has ever existed on Earth has circulated within the same closed system for billions of years. This places humanity in a strange position. We live on a planet so large that no individual can traverse it in a lifetime. Yet we are confined to a layer so thin that there is nowhere else to escape. Earth is vast in experience, but small in structure, and that is only the view from the inside. Earth only appears large when it is measured by our feet. To walk once around the equator requires a distance of about 40 kilometers. At an average walking speed of 5 kilometers per hour, walking 8 hours a day without rest. It would take nearly 3 years to complete a full circuit. 3 years is long enough for a child to grow up, long enough for a career to change, long enough for a life to turn in another direction. On the human scale, it is a monumental journey, almost unimaginable. But the remarkable thing is this: that distance still lies within the limits of a single human lifetime. No technology is required. No miracles. Only time and legs. Earth is small enough that a creature weighing less than 100 kilograms, living a few decades, can walk all the way around it. This sounds ordinary until one realizes the planet is not large. In a physical sense, it is only large in a biological one. The same distance takes a modern commercial aircraft less than 2 days of continuous flight. For the International Space Station, moving at roughly 7 Zaven kilometers per second. Earth is circled in about 90 minutes. Not because Earth has become smaller, but because the scale has changed. This is the key. Point size is not an absolute number, but a relationship between an object and the observer measuring it. A room is vast to an ant. A street is long to a child. A planet is enormous to a species living on its surface. Humans evolved to perceive the world on scales of meters, tens of meters, kilometers. Our brains are optimized for survival, avoiding predators, finding food, recognizing faces, estimating distances sufficient to throw a stone or outrun danger. There is no biological reason for us to intuitively grasp whether 40,000 kilometers is large or small. And so, intuition consistently deceives us. Earth's surface area is about 510 million square kilometers. It sounds immense, but 71% of that area is ocean, most of it unsuitable for long-term habitation. The remaining land is fragmented by deserts, high mountains, dense forests, permanent ice. When these extreme regions are removed, the area truly favorable for human life amounts to only about 12% of the planet's surface. In other words, humanity does not live on Earth. Humanity lives within a small fraction of Earth's surface. If Earth were a vast city, humans would occupy only a few neighborhoods with suitable conditions. The rest is too hot, too cold, too dry, too high, too deep, or too unstable. We call it our planet, but in reality, we are temporary residents of a very narrow zone. The feeling that Earth is vast arises because everything familiar lies within that thin slice. A few hundred kilometers between cities already feels far. A transcontinental flight is tiring. An ocean separating two shores is enough to shape distinct cultures and histories. Yet all these distances lie on the surface of a relatively small sphere. From low Earth orbit, detail vanishes quickly. From a few hundred kilometers up, where Earth-observing satellites operate, national borders disappear. Cities become faint streaks of light. From the distance of the moon, the entire planet is a blue-white disk suspended in darkness. From farther away, it becomes a single pixel, not because Earth has changed, but because humanity is no longer the center of the frame. Scale determines perception. A pond is a universe to a tadpole. An ocean is an insurmountable barrier to ancient species. A planet is everything to a civilization that has not yet left its surface. But in physics, there is no privileged scale for any organism. Earth was not designed to feel large or small to us. It simply exists, with its size, regardless of how we perceive it. This explains why human history is so often tied to the illusion of control, living on a surface that appears endless. It is easy to believe resources are endless as well, that there is always more space. that the planet is large enough to absorb every mistake. But that illusion only survives while scale remains locked within personal experience. When the scale changes, the illusion collapses. On geological scales, massive mountain ranges are only temporary wrinkles. On planetary scales, continents are slow-moving plates atop hot rock. On astronomical scales, Earth is nothing more than a grain of dust orbiting an ordinary star. And, on the human scale, all of this is compressed into the world. There is no contradiction here, only confusion of perspective. Earth is not large because of how much area it has. It is large because all of our experience is trapped within it. A fish does not know the ocean is small until it sees the sky. A species living on a surface cannot naturally perceive the true size of its planet without leaving it. Only with distance does the truth emerge. And that truth is simple. Earth is small enough not to be central, even within its own system. Recognizing this does not make Earth less important, but it shatters a dangerous assumption that the planet is a default backdrop, a permanent stage, a fixed foundation for every human story. In reality, it is merely a finite object with a defined size, existing within a much larger structure. We feel Earth is vast because we spend our entire lives within a thin slice of it. But physics does not care about feelings, and when feeling is stripped away, what remains is a planet that is not large, not central, not privileged, only just sufficient for life to exist. The moment Earth truly loses its sense of largeness is not when compared to humans, but when placed beside the nearest object in space, the Moon, a body that, from the ground, appears close enough to touch with one's eyes. The average distance between Earth and the Moon is about 384. Nil kilometers. This number is difficult to grasp until translated into everyday terms. If a straight road connected the two, a car traveling continuously at 100 kilometers per hour would need more than 160 days without rest to reach the end. Light, the fastest thing in the universe, takes more than a second to cross it. And throughout that entire span, there is almost nothing. No air, no sound, no support, only vacuum. What makes this distance unsettling is not the number itself, but its structure. If all the other planets in the solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune were lined up end to end by diameter, they would fit comfortably within the gap between Earth and the Moon, with room to spare. This is not metaphor but simple geometry. The combined diameters of those 7 planets total about 233,000 kilometers, significantly less than the average Earth-Moon distance. This shatters a deep illusion that celestial bodies are close together. In reality, the solar system is not compact but extremely sparse. Objects exist not because they are near one another, but because gravity is strong enough to hold them in orbit across vast emptiness. Even the most famous visual relationship between Earth, Moon, and Sun, a total solar eclipse, is a rare coincidence. The Sun's diameter is about 400 times larger than the Moon's, but it is also about 400 times farther away. This coincidence makes the two disks appear the same size in the sky. No physical law requires this. There is no design here. It is simply a brief moment in cosmic history, and it will not last. The Moon is drifting away from Earth at about 8 centimeters per year. In a few 100 million years, total solar eclipses will no longer occur. An experience that feels eternal is, in reality, a very short phase. When the viewpoint shifts from the Moon to the Sun, scale breaks completely. Earth's diameter is about 12. 742 kilometers. The sun's diameter is about 39 million kilometers. Lined up by diameter, it would take about 109 Earths to match the sun's width. But diameter is deceptive. Volume is where the difference becomes almost impossible to imagine. The sun could contain about 3 million Earths. All oceans, continents, atmosphere. The entire history of life and human civilization occupy 1/1,000,000th of the space of the star. This planet orbits. If Earth were a grain of sand, the sun would be a metal sphere weighing tons, and even this does not reach the greatest imbalance. The sun contains about 86% of the total mass of the solar system. All planets, moons, asteroids, comets, dust, and gas combined make up only about 0.6%. In other words, dynamically speaking, the solar system is almost entirely the sun. Everything else is minor noise within its gravitational field. This leads to a stark consequence if Earth were to disappear. The solar system would hardly change. The orbits of the other planets would remain stable. The sun would continue its nuclear fusion. Jupiter would still dominate the outer regions. There would be no collapse, no significant dynamical void. Earth is not a pillar of this system. It is merely a fortunate rocky planet occupying a position that causes no disruption. The distance from Earth to the sun, averaging about 150 million kilometers, is defined as 1 astronomical unit. Light takes more than 8 minutes to cross this distance. That means every ray of sunlight you see belongs to the past. If the sun were to shut off at this very moment, Earth would continue to exist for 8 brief minutes, unaware that its energy source had vanished, not because there was no warning, but because the universe has a speed limit. At the scale of everyday life, this number becomes absurd. A car driving without rest would need nearly 300 years to travel from Earth to the sun. A commercial airplane would require more than 19 years. Even the fastest spacecraft ever launched, the Parker Solar Probe, which reaches speeds exceeding 430 km a perihelion, still takes months to approach the sun's vicinity. There is no such thing as near in space, only distances that differ in degrees of enormity. Placed in this context, any notion of centrality becomes difficult to defend. Earth does not lie at the center of mass. It does not govern orbits. It does not serve a structural role. It exists because there is no physical reason to remove it. That is all. If the solar system were a stage, the sun would be the light source, the gravity, the rhythm. The planets are supporting actors in orbit, each carrying its own story, but none controlling the performance. Earth is not the protagonist. It is simply one of the rare rocky planets that has not yet slipped beyond the boundary of habitability. This does not make Earth insignificant, but it does erase a common assumption that our existence is tied to physical importance. In reality, physics is entirely indifferent to life. Gravity has no awareness of biology. Orbits do not care about history. Nuclear fusion does not distinguish between living and lifeless planets. Earth was not placed here because it is special. It became special because it has not yet been eliminated from the game. Within the solar system, there are planets too close, where water cannot persist, planets too far, where temperatures never rise above freezing, planets massive enough to retain atmospheres, but that retain the wrong kinds of gases, worlds that once had favorable conditions but lost them over time. Earth is simply a planet that has not yet fallen into any of these extremes, and that state is temporary. Viewed from within, it is easy to believe Earth is a solid foundation for everything. But when placed correctly within the solar system, that foundation becomes a small point orbiting a massive nuclear reactor far enough not to be incinerated, yet close enough not to freeze. There is no wide safety margin, no generous buffer. One does not need to leave the solar system to see how fragile Earth is. It is enough to look at neighboring worlds, places that once lay close to Earth-like conditions, but slipped away in different directions. Mercury is the closest planet to the Sun. Its diameter is only about 880 kilometers, nearly 3 times smaller than Earth's. Its proximity causes daytime surface temperatures to exceed 430 degrees Celsius, while nighttime temperatures can fall below 170 degrees Celsius. There is no significant atmosphere to retain heat, no oceans to redistribute energy, no magnetic field strong enough to provide protection. This temperature contrast is not a secondary detail. It is the direct consequence of insufficient mass and excessive proximity. Mercury is not unlucky. It is simply too small to hold on to what long-term stability requires. Venus is more dangerous because it presents a deceptively familiar scenario. In size and mass, Venus is nearly Earth's twin. Its diameter is only about 5% smaller. Its surface gravity is comparable. By the numbers alone, there is no obvious reason these two planets should be so radically different. Yet Venus is a textbook example of how a small deviation can lead to total catastrophe. Average surface temperatures reach around 460 degrees Celsius, hot enough to melt lead. Atmospheric pressure is roughly 90 times that of Earth, comparable to pressure nearly 1 kilometer beneath the ocean. The sky is veiled by clouds of sulfuric acid. There is no liquid water on the surface, no climate-regulating cycle. The cause lies not in size, but in feedback. Venus receives about 30% more solar energy than Earth. That number sounds modest, but it is sufficient to trigger a runaway greenhouse effect. Rising temperatures cause water to evaporate. Water vapor is a powerful greenhouse gas, driving temperatures even higher. The loop continues until the oceans disappear entirely. Ultraviolet radiation breaks apart water molecules. Lightweight hydrogen escapes into space, and oxygen reacts with the surface. Once the water is gone, there is no path back. What is striking is that there was no dramatic moment, no doomsday, only a sequence of slow changes that could not be reversed. Once the threshold was crossed, the planet had no return route. Mars represents a different kind of failure. About half Earth's diameter and only about 10% of its mass. Mars may once have hosted liquid water, rivers, even shallow oceans. The evidence is still etched into its surface valleys. Dry riverbeds, mineral deposits formed in water. But Mars lost what Earth retained: a global magnetic field. As its core cooled and ceased vigorous motion, the magnetic shield vanished. The solar wind, a stream of high-energy particles, began to erode the atmosphere. This process unfolded over hundreds of millions of years, quietly, without explosions. Yet inexorably, the atmosphere thinned, pressure dropped, and liquid water became unstable. Eventually, Mars turned into a cold desert, where water exists only as ice or vapor. Here, the difference lies not in position, but in mass and internal structure. Mars simply was not large enough to keep its internal engine running long enough. When we look at the gas giants, the contrast shifts again. Jupiter, Saturn, Uranus, and Neptune did not fail to retain gas. On the contrary, they retained too much. Their massive gravity allowed them to gather hydrogen and helium from the protoplanetary disk. forming worlds without stable, solid surfaces. Pressure rises rapidly with depth, reaching levels that would crush all familiar biological structures. Storms persist for centuries. Temperature and pressure change with depth in ways that prevent any surface-based ecosystem from forming. These planets are not unfortunate. They simply followed a different path dictated by physics. When a planet becomes large enough, it does not turn into a bigger Earth. It becomes something else entirely. Viewed across the entire solar system, there are not many options. Too small, and the atmosphere escapes. Too close, and water evaporates. Too far, and everything freezes. Too large, and the solid surface disappears. Earth occupies a very narrow band between these extremes, not at the center, not in a position of absolute safety, simply where conditions have not yet conflicted. And the crucial point is this: there is no large margin for error. A slight change in distance, a small difference in mass, a geological event that shuts down the core too early, an unchecked climate feedback loop. Any one of these would be enough to push Earth into a different scenario. And those scenarios are already present around us. Not in theory, but on real worlds. This dismantles a common assumption that Earth is the inevitable outcome of physics. Earth is not the default. It is a case that has not yet failed, not yet been pushed out of the habitable zone, not yet slipped from equilibrium. And because it has not failed, it permits something exceedingly rare: time. Time long enough for complex chemistry to arise. Time long enough for life to evolve. Time long enough for a species to begin asking questions about its own planet. But the surrounding planets are constant reminders that none of this is guaranteed. Physics does not favor. Orbits do not forgive. A planet does not retain habitability because it deserves it, but because natural processes have not yet eliminated it. Earth does not stand on solid ground. It stands on a dynamic, thin, temporary balance, just as other worlds once did, before tipping to the other side. After leaving the solar system, the sense of distance changes completely, not by becoming slightly farther, but by crossing into a regime where human intuition almost entirely fails. The closest star to Earth is Proxima Centauri, a faint red dwarf belonging to the Alpha Centauri system. The distance from Earth to it is about 24 light years. The phrase sounds familiar, but the number only gains meaning when converted. 1 light year equals nearly 46 trillion kilometers. Multiplied out, Proxima Centauri lies roughly 40 trillion kilometers away. This is not merely far. This is distance so extreme that all everyday comparisons collapse. If the distance from Earth to the Sun, 150 million kilometers, is taken as a familiar unit, then Proxima Centauri is about 268. 000 times farther away. A simpler visualization: if the Earth-Sun distance were scaled down to 1 meter, the nearest star would be more than 268 kilometers away. Not in the same city, not in the same country, but somewhere entirely different on the map. At this scale, the solar system no longer feels like a system. It resembles a solitary house in a desert, where the nearest neighboring house lies beyond sight, beyond hearing, beyond any realistic reach. Speed offers little help. Voyager 1, the most distant human-made object, was launched in 1977 and has now passed beyond the Sun's direct influence. After nearly half a century, it has traveled about 24 billion kilometers. That number sounds impressive until placed next to interstellar distances. At its current speed, Voyager 1 would need roughly 70,000 years to reach Proxima Centauri, and that assumes that we're heading in the correct direction, which it is not. 70,000 years is not the timescale of a civilization. It exceeds the entire history of Homo sapiens. By the time Voyager 1 reached the nearest star, if it still existed, Earth would be a completely different planet, or humanity might no longer exist at all. Even the most optimistic scenarios fail to change the nature of the problem. A hypothetical spacecraft traveling at 10% the speed of light, far beyond any existing technology, would still require more than 40 years to reach the nearest star. 40 years is not a journey. It is a lifetime. And that is only the closest star. This distance produces a cold consequence. Earth is effectively invisible to the rest of the galaxy, from Proxima Centauri. Earth cannot be directly observed by any telescope we can reasonably imagine in the near future. The light reflected from Earth is far too weak, completely drowned out by the glare of the sun. The planet emits no distinctive signal that would mark its existence. No signposts. No indication that life exists here, let alone intelligence. If a civilization existed around a nearby star, they would not see Earth, at best. They might detect the sun as an ordinary star with minor spectral noise. Earth, with all its history, oceans, biosphere, and wars would leave no sufficiently clear trace. This isolation is not psychological. It is a physical consequence of space itself. Radio waves, the farthest reaching communication humanity has ever used, fade with the square of distance. After a few light years, signals become indistinguishable from cosmic background noise. Earth's earliest radio broadcasts have been spreading into space for more than a century, but at interstellar distances, they have already faded to near non-existence. This shatters a common fantasy that Earth is a bright point in the universe, being observed from somewhere else. Reality is the opposite. Earth is an extremely weak emitter, submerged in the galaxy's background noise. No one is watching. No one is waiting for a signal. There is no cosmic audience. Even light itself fails to convey presence. Sunlight reaches Proxima Centauri after more than 4 years, carrying information about Earth from 4 years earlier. But that information lacks detail. A slightly offset point of light. A minuscule spectral variation. Nothing more. Isolation is not only distance, it is the absence of interaction. In everyday life, two people far apart can still communicate because space is filled with infrastructure. In the universe, space is empty. No wires, no networks, no shortcuts. This leads to an uncomfortable conclusion physically. Earth is a closed system. What happens here has almost no effect on the rest of the universe. And the universe, in turn, has little direct effect on Earth. There is no supervision, no intervention, no out there ready to respond. From this perspective, stories about being discovered, observed, or rescued belong more to imagination than science. Space does not operate like a social network. It does not care about the existence of a small, rocky planet orbiting an average star. This isolation also clarifies something else. Every problem Earth faces must be solved on Earth. There are no nearby neighbors, no place to move to, no easy backup plan. Even in scenarios of planetary expansion, humanity remains bound by distance, energy, and time in nearly absolute terms. On interstellar scales, Earth is not just small, it is alone. And this solitude is neither tragic nor romantic. It is simply a physical fact. A rocky planet carrying all known life, drifting in a void where distance is not merely an obstacle, but an insurmountable barrier. If interstellar distance renders Earth isolated, Then expanding the scale to the galactic level produces something else entirely. Earth ceases to be a place. It becomes a negligible detail within a structure too vast for human intuition to grasp. The Milky Way, the galaxy we inhabit, has a diameter of roughly 100,000 light years. This number gains meaning only when placed alongside our position. We are not at the center, not at a clearly defined edge. The solar system lies in a minor spiral arm called the Orion Spur, about 26,000 light years from the galactic core, a peripheral, sparsely populated, quiet region, more suburban than metropolitan. A common astronomical analogy illustrates this. If the Milky Way were scaled down to a disk the width of the United States, the solar system would be smaller than a grain of sand. And Earth within that grain loses all proportional meaning. It is not merely very small. It falls outside descriptive language. This is not just a shocking comparison. It has concrete physical implications. The Sun, along with its entire planetary system, orbits the galactic center at about 230 kilometers per second. One full orbit takes roughly 250 million years. The last time the solar system occupied this position in its galactic orbit, Earth had no dinosaurs. Complex life had not yet appeared. In other words, the entire history of humanity, from mastering fire, building cities, inventing writing, to launching the James Webb Space Telescope, amounts to only a tiny fraction of a single galactic year. Earth does not move in step with the universe. It drifts through timescales utterly incompatible with human life. This becomes evident in how we observe the galaxy. When radio and infrared telescopes began mapping the Milky Way, an uncomfortable truth emerged. We cannot see the entire galaxy from inside it. Like standing in a forest and attempting to map the whole forest using only sight, dust, molecular clouds, and distance obscure much of the galactic structure. Even estimating the number of stars in the Milky Way remains uncertain between 100 and 400 billion, an error margin so large that in most other fields it would be unacceptable. Here, it reflects observational limits. Among those hundreds of billions of stars, the Sun is an ordinary G-type star. Not large, not rare, not unusually bright. It does not lie in a major star-forming region, not near the central black hole, not in any structurally significant location. A mid-sized star in a mid-sized galaxy. One event often cited to illustrate this insignificance occurred in 1977, when Voyager 1 was launched to study the outer planets. As it exited the solar system, Carl Sagan proposed turning the camera back toward Earth. In 1990, from a distance of 7 billion miles, the image known as pale blue dot was captured. Earth in that image is not a globe, not a clearly visible point. It is a faint pixel, embedded in a streak of scattered light caused by lens flare from the Sun. Without annotation, no one could identify which pixel represents Earth. And the crucial point is this: 7 billion miles is nothing on galactic scales. At distances of just a few light years, Earth would not be a pixel. It would not exist in the data at all. Astronomers searching for exoplanets do not see planets. They detect minute stellar wobbles, or fractional dips in brightness when a planet passes in front of its star. Earth, viewed from across the galaxy, would not produce a signal strong enough to stand out. What does this mean? It means that if a civilization on the far side of the Milky Way possessed technology comparable to ours, they would have no way of knowing Earth exists, not because they lack intelligence, but because physics forbids it. This sense of insignificance intensifies when the scale expands to the observable universe, the Milky Way is just one of roughly 2 trillion galaxies. Many are larger, brighter, older galaxies in which the Milky Way itself would appear as a faint smudge from afar. The James Webb Space Telescope has captured galaxies that existed just a few 100 million years after the Big Bang. The light from them has traveled more than 13 billion years to reach us. When that light began its journey, Earth did not exist. The solar system had not formed. The heavy elements necessary for life had not yet been fully created. Those galaxies have changed shape, collided, merged, and evolved throughout the time their light traveled toward us. What we see is not them as they are, but ancient records of what they were. The universe does not allow us to see its present, only its past. At this scale, Earth is not merely small, it is out of sync. It appears late in cosmic history, in a quiet region, within an unremarkable galaxy, around an ordinary star. Nothing in the universe's structure suggests this place is special. If the entire observable universe were shrunk to the size of Earth, the Milky Way would be smaller than an atom. And Earth, within that analogy, would lose any coherent physical meaning. It would be swallowed by scale itself. This leads to a cold but essential conclusion: the universe was not designed around Earth. There is no priority, no center, no indication that this place was targeted, and it is precisely here that a paradox begins to form. If Earth is so small as to approach invisibility, if it holds no central position in space or time, then why does everything we know about life happen here? If scale were the only measure, Earth would have no reason to be noticed. It is not large, not central, not located in any special energetic region of the galaxy. But science does not measure specialness by size. It measures conditions, and viewed this way, Earth diverges from the rest of the universe in a very different manner. As of now, among the thousands of known exoplanets, only one place is confirmed to host life. Not because others are uninteresting, but because only here do we have direct evidence. Every organism ever observed, from acid-dwelling bacteria to blue whales, from the Amazon rainforest to microbes in Antarctic ice, belongs to the same planet. This fact sounds trivial until placed in cosmic context. The universe contains hundreds of billions of galaxies. Each galaxy holds hundreds of billions of stars. Many of those stars host planets. Some lie within zones where temperatures allow liquid water. But life does not automatically arise simply because temperatures are suitable. Earth is not merely warm enough. It achieved a rare sequence of conditions simultaneously. Earth's distance from the sun places it in the so-called Goldilocks zone, not so close that water evaporates entirely as on Venus, not so far that it freezes permanently as on Mars. But this is only the first condition. Venus may once have held water. Mars once had rivers, lakes, perhaps shallow oceans. Both lost them. The difference lies in factors not easily seen from afar. Earth has just enough mass to retain its atmosphere for billions of years, slightly smaller, and gases would gradually be stripped away by the solar wind, as happened on Mars. Slightly larger, and the planet would retain large amounts of hydrogen and helium, becoming a Neptune-like world with no solid surface for complex life to inhabit. Beneath the surface, Earth possesses a moving liquid metal core. This motion generates a planetary magnetic field, an invisible but critical shield. The field deflects charged particles from the solar wind, preventing atmospheric erosion and direct radiation bombardment. Mars once had such a field. When its core cooled and the field weakened, the atmosphere began to vanish not in a day, but over hundreds of millions of years. slowly enough that nothing seemed wrong until everything was gone. Earth also possesses a rarer feature, plate tectonics. The surface is not a dead shell, but a collection of massive plates drifting atop the slowly flowing mantle. This movement recycles carbon and regulates climate over geological timescales. As mountains erode, carbon dioxide is drawn out of the atmosphere. When volcanoes erupt, carbon is returned. This is not a perfect balance, but it is sufficient to keep Earth's average temperature within a range that allows liquid water and complex chemistry to persist for billions of years. Many rocky planets may lack this mechanism entirely. No recycling, no regulation. Once climate shifts, it does not return. Then there is the Moon. Compared to Earth, it appears secondary. But dynamically, its role is substantial. The Moon stabilizes Earth's axial tilt. Without it, the planet's tilt could vary wildly over time, driving extreme climate shifts. Instead of familiar seasons, Earth might experience global ice ages alternating with severe heat, never stable long enough for complex ecosystems to develop. None of these factors make Earth chosen. They merely show that a very specific chain of conditions occurred together, not by purpose, not by design, but because the universe has enough time and enough trials for a few rare combinations to succeed. What truly distinguishes Earth is not that it hosts life, but that life had time to become complex. Life appeared on Earth relatively early, just a few 100 million years after conditions allowed liquid water, yet it took nearly 4 billion years for simple bacteria to evolve into self-aware organisms. During that time, Earth was not reset by giant impacts, not sterilized by its star, not frozen permanently. It remained stable enough for biological history to accumulate, layer upon layer, instead of being repeatedly erased. A perspective often raised by astrobiologists is this: if Earth's history were rewound and replayed, the outcome could be entirely different. Life might still exist, but not necessarily intelligence. There is no guarantee that a species capable of questioning the universe is an inevitable result. And here, the paradox becomes clear. Earth is not important because it is large. It is important because it is so far the only place where the universe has produced beings capable of understanding that the universe exists. On physical scales, Earth approaches invisibility. On biological scales, it is the entire stage. Every DNA sequence ever decoded, every ecosystem ever studied, every fossil ever unearthed belongs to the same location. There is no comparative data set, no control sample. This does not make Earth sacred, but it makes one thing undeniable. Small does not mean trivial. In a universe vast enough to be indifferent, value does not arise from scale, but from the fact that something has happened and continues to happen against ordinary probability. If you ask most people whether Earth has abundant water, the answer will almost certainly be yes. From airplane windows, oceans stretch beyond the horizon. From satellite images, blue dominates the planet. In everyday life, water flows steadily from taps. Rain arrives with the seasons. Rivers still run through cities as if unchanged for thousands of years. Intuition says water is not something to worry about. Science says the opposite. In 2002, scientists at the USGS performed a calculation that seemed almost pointless, gathering all the water on Earth, including oceans, glaciers, groundwater, rivers, lakes, and even water vapor in the atmosphere, and compressing it into a single spherical volume. The result was shocking not because it was wrong, but because it was so precise. That sphere would have a diameter of only about 385 kilometers, or roughly 860 miles, compared to Earth's radius of more than 300 kilometers. All the planet's water amounts to a small lump resting on the surface. This immediately shatters a foundational intuition. Earth is not a water planet, but a rocky planet with an extremely thin layer of water coating its exterior. But even within that thin layer, the portion usable by civilization is far smaller still, about 97.5% is salt water, unsuitable for drinking or agriculture without energy-intensive processing. Of the remaining 5% of fresh water. Most is locked away in the ice sheets of Greenland and Antarctica or buried deep within geological layers. Surface freshwater rivers, lakes, wetlands accounts for less than 0.1% of Earth's total water. All of agricultural history, urban development, warfare, and the sustenance of 8 billion people depend on an amount of water equivalent to a thin film of moisture on the planet's surface. This is not speculation. It is clearly reflected in recent climate events. The prolonged drought in California from 2012 to 2016, for example, was not caused by Earth running out of water, but by disrupted distribution. Snowpack in the Sierra Nevada melted earlier. Rainfall arrived at the wrong times, and water storage systems could not adapt quickly enough. The result was that millions of people lived on a water-rich planet while suffering severe water shortages. At larger scales, climate reveals a similar fragility. During the most recent ice age, global average temperatures were only about 5-6 degrees Celsius lower than today. That number sounds small, yet it was sufficient to cover much of North America and Europe in ice. Lower sea levels by more than 120 meters, and confine humans to narrow habitable regions. A difference of a few degrees at the global scale is not a mild variation. It is a restructuring of the entire planet. Modern climate science reveals a striking reality. Earth can maintain climate stability over long periods, but only within a very narrow energy range. The system depends on a balance between incoming solar radiation, heat absorbed by the oceans, reflection by clouds and ice, and greenhouse gas concentrations. When one component is pushed too far, too quickly, the entire system responds in a cascade. The oceans provide the clearest example. About 90% of the excess heat generated by modern climate change is absorbed by the oceans. This temporarily prevents Earth from warming as rapidly as it otherwise would. But the cost is heat accumulation in seawater, altering ocean currents, increasing acidification, and disrupting food chains. The mass die-off of coral reefs over recent decades is not a localized accident. It is a physical signal that the system has been pushed beyond its familiar state. Once again, Earth is not about to die. The planet has endured periods far hotter than today and continued to exist. The issue is that the ecosystems on which humans depend are not designed for those states. Agricultural, urban, and industrial civilization emerged only during a rare, stable climatic window lasting about 11,000 years, a blink of an eye in geological time. When all of this is considered together, an unavoidable conclusion emerges. Earth is not a vast reservoir of resources to be gradually extracted, but a finely balanced system in which water, climate, and ecosystems exist within very narrow limits. These limits are not imposed by ethics, but by physics, chemistry, and biology. Standing on the ground, it is difficult to sense that the planet is aging. Mountains appear immobile, horizons unchanged. Today's sky little different from yesterday's. Human intuition frames Earth as something that has long been stable and will remain so far into the future. But that intuition collapses completely when Earth is placed on its true time scale. Earth formed about 5 billion years ago. The number is so large that the human mind cannot directly visualize it. So we subconsciously compress it into a vague notion of a very distant past. Yet, for most of that time, Earth bore no resemblance to the world we inhabit. Its surface was once a magma ocean, its air toxic, its skies filled with ash and meteorites. The planet existed for hundreds of millions of years before any stable oceans formed, and billions of years before anything like today's green world appeared. Life emerged relatively early, around 8 billion years ago. But for nearly 3 billion years afterward, Earth hosted only simple life forms. No forests, no large animals, no sounds beyond wind and waves. An external observer during that span would have had no reason to think this planet would ever become home to a technological civilization. The diverse, complex biosphere we recognize appeared only relatively late. The Cambrian event, around 540 million years ago, is often described as an explosion of life. But the significance lies not in life's appearance, but in the rise of complexity. Earth functioned for an immense span without animals, and certainly without intelligence. Dinosaurs, often seen as symbols of Earth's deep past, were in fact only one long chapter, not the main one. They appeared about 230 million years ago and dominated the planet for more than 160 million years. During that time, continents split and collided. Sea levels rose and fell. Climates shifted repeatedly. Dinosaurs adapted, evolved, and diversified without any need for intelligent life. Then, in a geological instant, it ended. About 66 million years ago, an asteroid roughly 10 kilometers in diameter struck Earth, releasing enough energy to alter the global climate. Dust and sulfur filled the skies. Temperatures dropped. Food chains collapsed. Roughly 3/4 of all species vanished. Earth did not collapse, but the dinosaurs' world did. What matters is that this event was not an extraordinary accident beyond natural law. Before and after it, Earth experienced multiple mass extinctions, each wiping out the majority of existing life. The largest, about 252 million years ago, nearly emptied the oceans and land surface of life. Recovery took tens of millions of years. There is no indication Earth regretted or corrected anything. It simply continued operating. In this picture, humans appear extremely late. The genus Homo has existed for roughly 2 million years, Homo sapiens for only about 300. Ling Ling Ling, all recorded history writing, science, cities, nations. Technology fits within the last 10 to 12,000 years. If Earth's entire history were compressed into a single year, modern humans would appear in the final minutes of the final day, and all written history would occupy the last few seconds before midnight. This overturns a deep assumption we often carry, that human presence is an inevitable outcome of Earth. The geological record shows the opposite. Earth existed for nearly all of its history without us, and there is no physical evidence that the planet requires humans to continue existing. Statistically, the dominance of a species for a few 100,000 years, followed by extinction, is entirely normal. Most species that ever lived on Earth are extinct not because they failed, but because environments changed, randomness intervened, and forces far larger than any organism's adaptive capacity took effect. Humans are not Earth's default state. We are merely a very recent chapter in a story spanning billions of years with no promise of how long that chapter will last. From the outside, Earth appears calm, a blue sphere quietly orbiting the sun. No visible explosions. No immediate global catastrophes. This calm creates a dangerous illusion that the planet is stable and safe by default. The scientific record tells a colder, more honest story. Earth has never been a gentle environment. It has only experienced relatively calm intervals, separated by disruptions large enough to rewrite the entire history of life. The only difference is that humans have lived entirely within one of those rare calm windows. Beneath our feet, the planet continues to operate violently. The thin crust humans inhabit consists of massive tectonic plates, slowly drifting atop a molten mantle. They collide, slide past one another, are forced downward and melted, releasing centuries of accumulated energy in mere seconds. The largest recorded earthquakes have not only destroyed cities, but also shifted Earth's rotational axis by tiny yet measurable amounts. In 2011, the offshore earthquake near Japan not only triggered a tsunami and the Fukushima nuclear disaster, but also slightly accelerated Earth's rotation, shortening the length of the day by a few microseconds. On human scales, this is meaningless. On planetary scales, it reminds us that solid ground is part of a dynamic system that never rests. Earthquakes and volcanoes are often viewed as localized disasters. The real threats come from rarer events that, when they occur, exceed any civilization's capacity to adapt. Supervolcanoes are one example. The last Yellowstone eruption, about 640,000 years ago, expelled thousands of cubic kilometers of material, blanketed much of North America in ash, and altered global climate for years. Humans did not yet exist. There were no cities to collapse, no supply chains to break. Earth passed through the event with no memory of it. If a similar event occurred today, the impact would extend far beyond natural disaster. It would represent a profound disruption of the systems civilization depends upon. No apocalypse required. A few years of crop failure, darkened skies, and a global temperature shift of a few degrees would be enough to destabilize social order. And these are only the threats from within the planet. From outside, Earth continues to move through a cosmic shooting gallery. Millions of small bodies orbit the sun. Most are harmless, but some cross Earth's path. Small impacts occur constantly. Tens of tons of material enter the atmosphere each day, burning up as meteors that humans often watch with romantic awe. History shows that not all impacts are small. In 1908, the Tunguska event in Siberia flattened more than 2,000 square kilometers of forest in seconds. Even though the object exploded in midair and left no crater, had it occurred over a modern city, the outcome would have been immediate and undeniable. This was not ancient history. It happened in an era of newspapers, railways, and telegraphs. Further back, larger impacts left indelible marks. The event that ended the age of dinosaurs is not remarkable because it was rare, but because it is clearly preserved in the geological record. Such impacts are part of planetary history, occurring on cycles of tens to hundreds of millions of years. For Earth, this is normal rhythm. For a species that has existed for less than 1 million years, it is a threat beyond intuition. What makes these risks worth considering is not that they are imminent, but that there is no rule guaranteeing they will not occur. Earth has no protective mechanism because humans exist. The planet does not distinguish between a natural ice age and a technological civilization. It responds only to energy, mass, and force. For the first time in geological history, a single species has become an agent comparable to natural forces. The biological record shows that current extinction rates are many times higher than the natural background level, not because of asteroids or supervolcanoes, but because of human-driven environmental change. This is not a moral judgment, it is a scientific observation. Earth has undergone 5 major mass extinctions. The 6th, if it is underway, differs in one crucial way. Its cause does not originate from space or from the planet's interior, but from a species living on this thin crust. This does not make humans all-powerful. It simply clarifies another truth. Earth is not safe by default, and it is not fragile because humans exist. It is fragile in the way all complex systems are fragile when pushed beyond the equilibrium conditions that sustain them for very long periods of time. There is no protective layer designed specifically for us. Earth does not promise safety, it only temporarily permits life to exist. After completing such a circuit of understanding, it is easy to fall into a sense of emptiness. A small planet, offset on the outskirts of an unremarkable galaxy, existing in a universe too vast to care about any individual entity. Humans appear late, exist briefly, are not guaranteed, not protected, judged purely by size, time, and probability. Earth carries almost no weight in the cosmic picture. But it is precisely at this point that a different question emerges, one that is no longer about physics or astronomy. Among everything we have observed, Earth is the only place where matter does not merely exist, but becomes aware of its own existence. Atoms forged in stellar cores, drifting through space for billions of years, eventually rearranged into structures capable of questioning the universe that produced them. Not because the universe needed this, but because, here, it happened. The photograph, pale blue dot, taken in 1990, shows nothing visually spectacular. Earth is just a tiny, faint speck, lost within a band of scattered light. What gives the image its weight is not the size of that speck, but the realization that everything that has ever mattered to humanity is contained within a point almost too small to see. Not because Earth matters to the universe, but because, at that point, the universe produced a place where meaning exists. The anthropic principle does not say that Earth was designed for life. It says something simpler and colder. We observe the universe as it is, because if it were different, we would not be here to observe it. There is no guarantee, no destiny, only a chain of contingent conditions stacking over billions of years, precise enough for a small planet to retain liquid water, an atmosphere, a magnetic field, and enough stability for complex life to emerge in time. This does not make humans central. It makes humans rare. In a universe where most matter blindly follows physical laws, the existence of a place where matter can think, remember the past, imagine the future, and assign value to its own existence is not self-evident. Consciousness, viewed this way, is not remarkable because it is powerful, but because it is fragile and not required to appear at all. Earth is not special because it is large. It is not special because it occupies any central position. It is special because, so far, this is the only place where the universe has looked back at itself, not through light or gravity, but through thought. This does not impose a sentimental moral obligation, nor does it demand blind optimism. It simply establishes context. If value does not arise from scale, then a small planet can carry immense value not in the eyes of the universe, but in the lived experience of the beings who exist upon it. Value does not come from how large Earth is. Value comes from the fact that, here, existence can be recognized as existing. Earth is not large, not thick, not stable in the way we intuitively perceive it. It is merely a small rocky planet, coated with a thin layer of water, kept alive by an atmosphere thinner than human intuition can comfortably grasp, drifting through a universe that has no concept of protection or favor. All scientific evidence points to the same conclusion: Earth is not central, not default, and our existence on this planet has never been guaranteed. And yet, on this small, fragile, unpromised world, life emerged, consciousness formed, and for the first time in the universe we know, matter began to understand that it exists. Earth is small, but this is the only place where everything that has ever mattered to us has ever happened.